Welcome to a review of Week 2 of Industrial PLC Applications. This week, we continued our look at PLC ladder logic and practiced the core skills needed to write, edit, download, and run a PLC ladder logic project and program. Let's review what we achieved specifically and embellish on or further explain some of the concepts. We began by looking at relay logic. Reading and understanding relay logic is still a vital skill required of electricians. The format and flow was adopted and is used for most PLC logic operations and formatting. Although not the focus of this course, you'll be writing PLC programs that operates and controls motors and solenoids, etc. with the same goals and the same operational features. With relay logic and ladder logic that followed it, all logic flows from top to bottom, left to right. All inputs are towards the left handrail, and all outputs, save and except for overloads, are on the right handrail. All devices are always shown in their shelf state. In this example, current flows to the motor starter M1 momentarily, but long enough for the current to energize the coil and thereby closing its contacts. When this happens, the contacts seal in the motor starter. This is an example of seal-in logic or low voltage release. It also initializes a timer relay, which we'll begin to study, and the concept of interlocking. Let's review some of the instructions we did this week. Set, or OTS. The set coil is a single bit of rule output or write instruction that once energized stays energized regardless of the state of the logic before it. It must be de-energized by another command instruction. It's not recommended for use for motor control, but it's often used as a memory bit to state a condition has occurred and must be cleared. The reset instruction, or OTR, is a single bit or rule output instruction that once energizes, de-energizes the named variable. It's often used to clear a memory bit. The reverse coil is a single bit output write instruction that de-energizes the associated variable. Often used in NOT logic, whereby an output is turned off by a set of preconditions. It is not recommended for motor shutdown circuits or logic that is controlled by low voltage release, a stop push button, or an MCR. During the walking lab, you were instructed to copy and paste a rung of logic that ended up duplicating an output's direct coil in another program, but then changed the triggering contact. This resulted in unusual and unexpected behavior. The PLC follows a simple routine protocol to handle inputs received, solve logical propositions, and sets the outputs as required. Collectively, this is called the program scan cycle. After startup, the PLC scans all the inputs and records them for comparison and logical resolution. Once the inputs are scanned, the PLC resolves the logic by applying the updated status of the inputs and formulating each rung's current status. Once all the logic has been resolved, every rung of every program in sequence, then the PLC turns on the appropriate output terminals. After completing the outputs, the PLC performs some internal housekeeping, such as updating system status, etc. It also performs all remote communications, sending updates via USB or Ethernet to a PC or to another PLC, and receives data from external IOs or PLCs or the PC. This broken circle cycle continues until the PLC is either shut down or is placed in program mode, whereby the outputs are turned off and the scan stops. However, housekeeping and communication activities continue as required. Because the outputs are not energized immediately upon a change of logical state, duplicating outputs can create unpredictable logic flow and execution. The rule of thumb is last order wins. We also started to look at some of the memory locations and how they function. We created a different form of memory location. In week 1, we learned that inputs and outputs were in reality just a single transistor deep inside the CPU that is energized, made true, or de-energized, made false. We also learned that an input can be repeated as often as required, and outputs can have as many associated contacts as needed to solve the logic. To begin with, we looked at real-world inputs and outputs, and found that real-world inputs and output variables are often referred to as addresses, since each input and output has a definitive terminal screw where a signal is received or a signal is transmitted. Furthermore, we discussed that I/O was contained in the global variables collection, and that any program in the project has access to them. Then, we programmed a new direct coil and created a DINT variable called program_step to name the direct coil. However, doing that, it created a problem triangle. This was caused by using the wrong size variable. Direct coils work on a single bool or a bit. A DINT is larger than a single unit. A DINT consists of 32 bits or bools. This means we have to take only a small part of the DINT. When we go to try to correct this attention triangle, when we click on the variable name, turning it blue, and right click, go variable selector. The selector by default is going to give us this program step as a bool. But above here it says bool in red. This is actually a search filter, and it has selected only the bools because we called up the variable selector from a bool instruction. Output, OTE, direct coil, reverse coil, they only operate on a single bit or a single bool. So if we get rid of the filter, and we're going to just leave that blank, it gives us everything. We happen to have a timer in there, plus a couple of bools, and it's suggesting this bool. However, there's already a variable with the same name, and that is not allowed. So we're going to get rid of that, and that gives us our DINT. So with the DINT, you can't put 32 bits into a single bit. It doesn't fit. So the arrow on the left-hand side dictates that we can open it to look at all of the components of this data type called DINT. And if we scroll down, we start at step 0 and we end up at step 31. So any of these are valid, and if I highlight one and just outside of your screen, it'll say OK. Look that up. So there's one. Hit OK, and our problem's been resolved. It now has our step 0 because this is one small component of the 32 bits that make up a DINT. We're going to get a little bit deeper into variables in an upcoming class. DINTs are memory constructs consisting of 32 contiguous bits or bools, 32 bits in a row. We can examine the DINT as one large number storage or a collection of individual like named bools. In order to program a single bool from a dint, the bools must be delineated from the dint. All variables greater in size than a bool can be reduced into its components, and a dot separates or delineates the component from the overall variable construct. This applies to all user-created variables. When you examine it, program step is the variable construct's name. The period is the delineator. It separates the name to each of the members. Past the period is the member, and in this case, program step is a construct of 32 bits, and 0 is the member bool. Other constructs can actually have more. I'm going to spend more time examining variables in detail and going over some of the other constructs, especially when we get into timers and counters. But for now, let's carry on with a review of week 2. Let's take a look at some of the programming we did. Many times our jobs as electricians means determining the work of others, or to correct problems with a ladder logic program. Editing allows you to make changes to a program or to a single contact or variable. So far, in the first 2 weeks, we have changed direct contacts to reverse contacts, direct coils to reverse coils, direct coils to set and reset. We've also changed the name of a variable and even the bit level of a variable. Just remember the adage, watch where you point that thing. When making edits and you're working on an instruction or the instruction's variable name, you have to be careful where you're pointing it. If you hit the instruction itself, a green box will appear. When you do that, you can change the instruction type. If you click on it and form a blue box, then you're focusing on the variable name that controls or writes to, reads from that particular variable name. Therefore, when it's blue, you're going to edit and change the variable. Up to this point, we have made single line rungs of ladder logic. These do not have any alternative execution paths, basically a single input contact in series with a single output coil. But in automation, there are often many alternative solutions or considerations to energize or de-energize output or change the program flow. The principal method here is to create a subrung or branch to offer an alternative solution or check. The example below provides 3 alternative solutions to energizing the direct coil run. Branching adds an infinite numbers of ways to control logic flow. There are 8 video links posted on Slate for some of the programming applications and more sophisticated uses of branches. I highly recommend you take the time to watch them. The most common branching circuit is the seal-in or latching circuit, much like we saw with our relay logic cousin. This logic works because there is a set of auxiliary contacts branched around the triggering input. These provide a feedback path that shorts out or jumpers out the triggering device, and the output remains on even after the trigger has been removed. In essence, the circuit becomes its own version of the set instruction. The difference here is the seal is defeated by placing the stop push button ahead of the trigger so that power is removed once the stop is pressed, therefore breaking the seal. When we duplicated our outputs, we ended up having unpredictable machine operation. You were introduced to something called the cross-reference utility. The cross-reference utility is a great resource and is used to find other locations of a variable. It can be accessed from any contact or coil anywhere in the project by right-clicking on the variable and then scrolling down to the browser selection. The cross-reference utility is used to determine the other locations a variable is used in the process. This allows you to jump to different runs to analyze how the variable is used. The last column indicates whether the variable is used as a read instruction or it'll be overwritten by a write instruction. As mentioned briefly before, read instructions are ones that the PLC only examines and records the values applied to the logic. Read instructions are considered non-destructive. That is, the data that is stored in a variable remains unchanged. Write instructions are ones the PLC will overwrite the value located in that variable location. Write instructions such as direct coils are considered to be destructive since the value stored at that memory location is overwritten and replaced with the current value, even if it's the same value that's already there. By now, you should have developed the primary skills and knowledge to be in programming on your own. We have covered everything from project and program creation to writing laddered logic with branches and outputs. Week 3 will have you doing your first exercise where you will create a ladder logic program that contains at least one seal-in circuit. We will also be starting our first lab, so be sure to be on time. Remember, when we do the lab, it is a singular, unassisted endeavor.